In our previous video, we performed data preparation or data preprocessing, what I refer to as exploratory data analysis, where we checked for missing values, the structure, shape, and size of our data, perform some visualization using Matplotlib and Seaborn libraries to check for distribution of our data, where we were looking for skewness and how our features are distributed. Now, remember that in the real world, data is actually daddy. And as a data scientist, sometimes you'll find some features in your data set. So for example, here, some of your features here might not just be numeric, uniformly numeric. You might find others are categorical. So you might need to convert that using one hot label encoding, right? Again, you might need to perform some scaling of the data. So as a data scientist, much of your work will be spent in preparing your data, right? So that you bring it to a form where you can move on to the next stage. So in this video, we're going to perform the third step, which is model building. Now that we've prepared our data, right, we've gained some insights. We've looked at how some features are associated with the dependent variable, which is price, right? So the next thing we're going to do here in model building is to partition our data into, we want to separate that into, features and our outcome or target variable. And then we split that into train and test sets, right? And then also we'll select a model. In our case here, we're going to look at linear regression and train that on our data. And then again, test the data on some test data, test set. And in some cases, you might need to tune your model to increase or improve the performance. So first, again, just make sure you import your libraries. So for here, I'm just going to click on that. So we're going to be using linear regression. Okay. Again, here, I've already imported this. So again, you can always import that. We need to make sure that we've stored or created our new data frame, okay, called US_housing. So we are just using the same data set. All right. So the first step here in model building is to split our data, right? So again, here in pandas, so we're using pandas here. So this double square brackets, just allows us to select these columns, right? And represent that as some data frame, right? So we're going to store that as X, right? And then also this will be, like a series, right? Anyway, so here we're just extracting. One of the reasons why we're doing this is because sometimes data might look like this, right? So you can see price is somewhere in the middle. Most times your target variable will always be the last column, but this one here, you can see it's somewhere in the middle. So we can explicitly select some of the features that we think we're going to be using in our model. So remember here, you can notice that we've already dropped the address. We don't think that will be impactful in our modeling. All right, now that we've done that, the next step is to split the data into train and test, right? So first thing is to import this module selection, and then we import this function or method that allows us to split, right? So we pass our X and Y, right? The one that we just created over here previously. And then we're saying we want to split the test set 60-40. So 40% will go to our test size, and the remaining 60% will be taken into X train, right? And Y train. And then the 40% will be X test and Y test we'll use for testing. So that's what this means. Now, to build our model, the first thing we want to do is to import our regression. We've already imported this library previously, but for demonstration, I'm just going to import here again. So this comes from the linear model, right? So if you go to the reference here, you can see these are all our, different functions that we use. Where is that? So here you can see we have our linear model, and you can see here, this is for regression, right? So our case here, we're going to be using linear regression. Okay, all this. So here we're just going to, so it just employs ordinary least squares, linear regression. Okay. All right, so once we have that, the next thing we want to do here is to instantiate this, right? So essentially we want to create a model, so and store it in a variable called lm, right? So we're creating an instance of linear regression model in object-oriented programming concept. Again, this is just a concept. We're creating a blueprint. So this is a class, right? So this will inherit the attributes and methods of this class here, or this function. Okay, and the two main methods are the .fit and .predict, right? That allows us to fit our model and predict on some new instance. So once we have a copy of this, we can inherit some of the attributes, right? And some of the methods that come from this class. So once we do that, the next thing is to fit our model, right? So here, .fit here, we pass two arguments, right? X train and Y train. So what this does is that we want to find the best parameters that minimize a given loss function and make our model fit the training data. So this is exactly what we want to do here. Okay. And then the other thing we can do here, so once we have our model here, right? So we can access some of the properties. So we can access the intercept property. But let me just talk a little bit about the fit here. So again, this is just a method that's used to fit the model, right? You're given a set of training data. Now the goal here for the .fit here, again, is just to find the rather minimize a given loss function, right? This loss function could be mean absolute error, depending on which you are using to, evaluate. The goal here is to, make sure there's minimum error between your predicted and your actual Y. Okay, predicted Y and actual Y. Now, these are two properties we can access. The intercept here, given this equation, y equals to mx plus b, here m will be your slope, right? That means slope of the line, and b is your intercept. So why do we extract the intercept? Again, the intercept here just allows us to, get the the value of y when x is 0. Okay. Now, another property or attribute we can access using the our model instance of our class linear regression is the coefficients, right? Now, these coefficients allows us, actually, these are just the weights of the features in the linear regression model. So it returns an array, and this corresponds to each of these attributes here. Okay, so I've used the pandas data frame just to give you a summary of how these coefficients look like, right? Now, these coefficients, it just contains the values of each of these features fitted in a linear regression model. Okay, so they actually represent the relationship between each feature, right? This feature and our target variable, right? Which is price. Now, you notice that we have all positive values. What that means is that an increase in the feature value is associated with an increase in the target value, in our case here, price. But when we have a negative value in our coefficient, what that means is that an increase in the feature value, right, just corresponds to, it's associated with a decrease in the target value. In our case here, it's just the price. Okay. So how to interpret this? What that means is that for every 1 unit increase in X variable, the Y value increases by the coefficient here. Okay, when all other variables are held constant. So picking an example here, let's pick maybe the area population. So what that means here is that keeping all features constant, an increase in 1 unit in area population. So think about this Y equals to mx plus b. We fix that with one of the features here, X, right? So, and then we're saying here, an increase in 1 unit in the area population. So multiplied by 1 increase here. Okay, 1 times the coefficient of that. Again, it just corresponds to an associated with an increase of $15, right? So that's what it means, right? All right, so now that we understand that, the next thing is to predict, use the predict method, right? So what this method does is just takes an input set of the feature value and returns a predicted target value. Okay. So the first thing we want to do here, so let's just extract the first 3 rows from our X train, right? So you can see these are the first rows, right? So it just contains the features, doesn't include the dependent variable price. Okay. Now, the goal of predict here is to try and, predict the Y here for our X train. But let's first of all predict X test, right? So we feed that and we call this variable Y_pred, right? And then we can predict this on the first 3 observations, right? So we can see now it returns an array with these values, right? Now, if we go to our Y test, right, and we access the first 3 values, so remember, this is our labeled Y, right, our test set. We can see here, there isn't much difference here. You can see this was our predicted value, 100, this is 1.3 million, 11,074. And this is actually 1,303,000, 339096. Okay. Same with this again. So we have there 1.23, we have here 1.25, 1.224, and this is 1.34. So not too far off. This is almost closer to the actual values here. So this is what the YPRED does. Okay. Now, to evaluate our metrics, we're gonna use the metrics function, or the metrics. We're gonna import the metrics, right? Again, we can create a function, right? This function just takes 2 values, Y test and Y predicted, and we're gonna be using this. So remember, from the metrics function. So if we go here, if we go to metrics, for example, right? So the metrics here, we can access all this. For regression metrics, we have, for example, mean absolute error, mean squared error, and so on and so forth. So for R square, we use R2 underscore. So we go back to our notebook. We can see that for mean absolute error, we use the mean absolute error. It comes from this function here, right? So again, we do that for MSE. Again, we use that and we pass our Y test and Y pred. So we are comparing the predicted Y and the actual Y. So for all this, and then for RMSE here, we're gonna use NumPy here to get this function square root, and then we square our squared error, because RMSE basically is just the square root of the mean squared error, which we already have here. Okay. Again, we have R2 score. We just access that for metrics. And then if you want to explicitly do that using the print function, rather than we're going to see an instance for this, then we can just go this route. Okay. So we print that, and we can already see that our R squared here is 91.64%, right? So this is what really tells us, right? Explains the prediction variance of our target. Is it better or is it worse, right? So in this case, it just tells us that the R squared of our linear regression is 91.64%, right? That's the variance of the housing price in the data. How much of that can be predicted by the model, okay? And then RMSE here simply just means that from the predictions on the testing set, the average difference for each prediction is $100,596. Okay. So again, we can also use the function that we created here to just generate the same metrics here. So this function we just call the evaluate here. We print that and it just generates for us the same thing. Then lastly here, we can visualize the data. So we can visualize the data. We can see now the model actually has done good prediction. There's a linear relationship between our predicted values and our our actual Y, right? So there's a linear prediction. Okay, so that just means that our model is doing good prediction. Then also we can create a histogram, right, of our residual. In fact, this is one of the assumptions, okay, of a linear regression. And what that means, it helps us to visualize. So this is proof that whenever we see a normally distributed residuals, it's proof that there's actually a linear relationship between, a linear relationship with the dependent variable. What that means also is that we're able to explain the relationship in our data. If it were not linearly, or rather, if it were not distributed, normally distributed, Gaussian distribution, then what that means, it's not able to explain the relationship in our data. Then lastly here, we can also compare the actual versus predicted. So again, here we just want to, so this is just trying to put everything in a data frame. It looks much better, it looks nicer. So here we just use the predict function. We've already looked at that. And then we just bring it here. So we just construct a data frame, right? Using a dictionary here. So the dictionary allows us to pack in the key value pair. So actually here we call the Y test, and predicted here we call the Y pred. And we tell our data frame that we want to just extract the first 10 values. So we pass 10 value here, okay, the value 10. And you can see here, there isn't much difference between the first observation. The actual was actually 1.3 million, 33, and the predicted value was 1.311. Same here, we can see there wasn't much, there was a minimum error between the two. So clearly here, our linear regression is doing a better job, fitting a line in our data. So it's generating a good model and minimizing that loss function. All right. So in summary, we've actually created a simple linear regression model. This model can actually be used to help predict the price of a house to a potential real estate agent, right? In our next video, we're going to look at other different algorithms and how they perform as well.